This is part 2 of lecture 8, which was on latest developments around Ethernet. But before I start the lecture, I want to make a couple of announcements. I have already put your assignment 4 up. Assignment 4 is a little bit hefty. Actually, last year this was like 2 1/4 of an assignment. Okay, but this time I just condensed that a little bit in one assignment. There are a lot of problems and about 29 questions about lecture 7 and lecture 8. Okay, but the good news is that these are all small problems, very, very short problems. So reserve some time for that to solve it. Then the other announcement is that the project is due to next Tuesday, project number 2. Now, I see that some people want to defer it to next Thursday, so that you have like 1 week between this assignment and that assignment, and then 1 week between that assignment and the next one. So I will make like that shift later on today, and I make an announcement in here. Okay. Due to next Thursday rather than next Tuesday for your project. So you have a little bit more time. And then you have 1 week for this new assignment. Another question was how many more projects are left. And there is one more project which is like socket programming, which is a relief easier one for the CS majors. Okay. And then in addition to that, we have like, I believe, 2 or 3 more assignments. Okay. One of those assignments is like going again to internet and do some search, which is again a little bit maybe time consuming. And then there is one assignment on the switches and the routers, and one assignment on the wireless, whatever I say. The one on wireless is very soft, just questions, things like that, no problems, because that's the end of the course, an introduction of the follow-up courses, at least that I teach. Okay. With that introduction, let me just go to your lecture number 8. Lecture number 8 was Fast Internet and Beyond. And if you remember from our previous lecture, we started with, we said that in this lecture we will talk about 100 base 802.3 variety of versions. And really that is the main part of this lecture 8, because the rest are like easier and little parts. So in the last week what we talked about really was 100 base T and 100 base X. T was the one which was on 4 wires and is the most popular. And X is the one which goes on unshielded twisted pair and fiber, which uses the really truly, it's like FTDI over Ethernet, the X part. Okay, T part is the new contribution in the like networking, which uses like can be used on Cat3. Okay, which is telephone wiring. So this week we talk about a little bit more details in this area. If we come in here, that was the outline of everything. Fast Ethernet, what we talked about last week. Now, this week I talk about these topics, each of them very small, like a couple of like overheads. One of them is the story of VLAN. We come back in VLAN implementation when we talk about bridges and routers. But today is like how the packet format changes. What we were discussing last week was that after Ethernet became successful and went all over the place, people were thinking about 2 things. One is how to change the physical medium to draw higher data rates. Okay, and get the features that they were into 802.5, for example. What were those features really? One of those features was they had priority in there. Priority was not useful, but anyways they had it. We will see that how they brought that into the format of Ethernet. And then full duplex operation in here is like point-to-point, which if you remember again, 802.5 was a bunch of point-to-points. If you go to full duplex, it's a better actually full duplex is a better point-to-point. It goes in each direction and has just like point-to-point connection. Then again, another issue which was not addressed in 802.5, but in other places people were very keen about it, was the issue of if you come inside the office, the first day you start networking. If you go, but networking, you don't see the things because the wires are behind the building. You have to think about the application. You have a telephone, you have a local area network. They are using different wiring. If you think like an engineer, you feel that this is dumb. Okay? And now that Ethernet is successful, people want to what? Put the voice on top of that. So they want to have PBX, which is local area voice-oriented network. You remember, PBX is like one telephone switch, which has lines which comes to every office. Okay, now I have Ethernet also in the same way. I have a switch and wires comes to every office. Why shouldn't I mix these two? Beautiful idea, huh? If you were a venture, you would drop a lot of money to implement that. Okay, they did it actually in mid-1990s, mid to late 1990s. They went for ISO Ethernet. They thought it's very, very successful. We will talk about that one too. Okay, that's another little trick. Then another little trick that they played is this 100 base T2. See, you're using 400 megabit per second, 4 pair of wires. And people don't like it. They think that 2 pair is like more solid. I mean, 4 is very strange. So a group started to work on what? 2 wires. In a sense, if you look at that pattern, these people who are working in these things to go to higher data rates or use less number of wires, these are people who were like modem designers. These are like physical layer people, communication theory people, information theory people. They used to design modems. In voice band modems, if you remember, lines were very, very expensive to lease. So people wanted to go to more complicated modems to pay less to the telephone company. So they created a body of knowledge for information technology, information theory, okay? Which is information theory is what which is really related to physical layer, signal processing, modulation techniques, huh? A lot of except properties in there, which is the food of a lot of PhDs in the past 20, 30 years. Okay, a lot, like 80% of the PhDs were around signal processing and information theory, because there are a lot of complex issues in there. One of the major applications was modem design technology, which was motivating all of these works. And then military application and radio modems. Okay, so anyways, they have that body of knowledge. Now they want to come in here and apply it gradually. Because at the time that they were doing that for the voice band modems, processors were very expensive and slow. So they couldn't go more than like 2400 bits per baud. Okay, but now every year the speed has doubled since 1970s. Okay, so now you can go to higher data rate. So here we are, that's the dilemma. Okay, that's what they face in terms of data rate. They take these technologies which basically were developed for voice band modems, now they implement it for what? For higher speed local area networks. Okay? And that's what will happen, which people start with going for 100 base T2. They get a little now complex in terms of modulation technique. 100 base T2, however, did not become popular. Okay? However, the technology that they were using in there, which was 2-dimensional signal constellation, later on came to gigabit Ethernet. They used it for gigabit Ethernet, and that one is working. Okay. In addition to that, in gigabit Ethernet, they are using, as I told you last time, complicated coding techniques, like trellis code modulation. which was originally again designed for what? Voice band modems. We don't go to that much of detail for trellis coding in this one. But if you want to learn about it, 532 is the course, okay, which has a lot of modulation techniques. And that's the trend then around there, okay, taking all the technologies and signal processing which were for low-speed modems, bring it to LANs, okay. And we go over VLAN and full duplex. These are two tricks that they played with the packets. And then we talk about ISO Ethernet, 100 base T2, and gigabit Ethernet, which are tricks that they played really in the physical layer. In here, you have another separation. You want to integrate the voice and data. Means you want to get a voice-oriented network to go to the what? A data-oriented network to go to voice-oriented. In order to do that, you have to change your medium access control. And that's what they have done in ISO Ethernet. Okay? So we just go over these things as applications, because earlier we have spent a lot of time on the physical layer. These are what we did last week. We talked about fixed, next, and things like that, and different type of categories of wire. This was the main thing that we covered in the last week, detail of this thing, which are two branches of 100 base called fast Ethernet. These are over 4 wire, these are over 2 wires. And then I told you about the codings that they used in them, which basically they use 4B, 5B, ML3 coding, and 8B, 60 coding. And that's what I described in the last lecture to you. And by doing 8B, 60 over 4 pair, they could go what? 100 megabit per second. By using 4B, 5B over 2 pair of fiber, they could go, and taking that one in tandem with ML3, they could go over 2 like shielded twisted pair or Cat5 for 100 megabit per second. This is what we did in the last week. Okay? So we told you what is this coding and how they came to 100 megabit per second with this type of wirings. Okay? This is the 4 pair of wiring. This is 2 pair of wiring. And then we talked about auto negotiations and two classes of repeaters. And this was the place that we left. Virtual LANs. Okay. Now, what is a virtual LAN? To start about it. And how did it start? It started in 1998 in IEEE 802.3 AC. Okay. If you remember, AB was what? They ended up with the Z. Z was gigabit. Okay. Then they went AB, which was another version of gigabit. And then they came AC. AC is VLAN, which is 1998. Now, the story of the VLAN is that they want to add a tag to the packets that identifies a sub-LAN. So if I come to WPI, for example, I have a bunch of different LANs that I'm connected to. Okay, I want to create different domains in there. Means that a bunch of LANs, a bunch of LANs, a bunch of LANs. Okay, now, in order to do that, I need to have a tag. Okay, that tag, how I can provide it in an environment that I have one unified tag only. Because in Ethernet, everything is only one unified tag. Okay? I mean, you have one packet format. Okay? How I can change that so that I can have different packets out of one packet. That's the story of VLAN and other things. So basically, the trick that they played with the VLAN is this thing that we have in here. The trick that they played for the VLAN was that this is the ordinary packet format of what? Of 802.3. It doesn't have preamp and doesn't have the start of the starting delimiter, because those are like physical layer related. The real MAC is this thing. You have destination address, you have source address, length, data, pad, and checksum. And this data length is how many bytes? It's 2 bytes. The data maximum length is what? 1500. So there are a number of other numbers that you can put in here which they don't address a length. Okay? With either of them, you can play a trick and add some features. One of those features, and one of the early ones, was VLAN. How they do the VLAN? That's it. What they do is that they take this source address destination, and no problem. They don't touch it. After that, they put a 2-byte, they add 2-byte rather than length in here. This 2-byte has this address, which is 8100. 8100 is bigger than 1500. Okay, they put it in here as address. So when this packet is read, destination address, source address, as soon as terminal reads it, terminal realizes that this is not a normal address. So if it is now equipped for VLAN, it tries to interpret that. Okay? And then after that, it interprets that as a new packet. And that new packet format is a VLAN new packet format, which has another tag in here. What is that tag in there? Tag is another 2-byte. So this is really control information that you have. This is like a flag to say that I am a VLAN. Okay. Now, when it comes in here, then what it does is it looks at 3 first bits, and these 3 bits are assigned to priority. If you remember, priority for 82.5 and 4 was also 3 bits. So this is equivalent to that. But it's a useless nearly bits. These are useless bits because nobody uses priority for this type of operation. But since every 10 years they do one addition to the things, they try to put something for reservation, for future. Then they have added 1 bit in here, this CFI. They call it canonical format indicator. This is another one of those unidentified. Bottom line, this bit was forced by 802.5 community to just say that this packet which is around is 802.5 or 802.3 in a sense. That's how they use it. Okay? So if you have a virtual LAN which is connecting through Ethernet, but at the end is 802.5, 802.5, you can use this bit to indicate that. Okay? And then after that, you have 12 remaining bits out of the 2 bytes. These 12 remaining bits is identifier or name of address of what? Your VLAN. After that, you're back to everything that you had before. Okay? Now, in order to operate with these things, with the VLAN, you have to have bridges. Okay? Bridges should know that this is a packet which is what? Which is a VLAN packet. Okay? And switches should know that, anything that you connect to. Because if they don't know, if they know that, they cut these 2 out and they leave the rest inside the LAN that they belong to. Okay? So this is how you should be. So the transmitter is aware, at the same time the bridges and switches have to be aware of that in order to manipulate it. Okay, and get it to the system. Okay. Now, so if you have a feature like that, which means that you have to now somehow go and tell the people who are designing the bridges that this is a format. So you have to somehow register this address. The community who registers this is what? 802.1. If you remember, 802.1 was the one which is for what? Related to bridges in the 802. So they go to the 802.1 queue, and in there, one queue come up with a set of instructions for the manufacturers of what? Of the switches and the bridges to include VLAN feature or not include. Okay? So the instruction comes from 802.1 queue. And basically that instruction says how to implement this thing and how to detect this address. Okay? And then basically when you do that, you have to have a bridge associated to that. And we talk about those type of things, as I said, when we talk about bridges. The same problems that you have for other bridges, you have for this one as well. You have to create a table for routing. Okay? And you have to find your route. So that recommendation comes out of what 802.1Q, 802.1Q. Okay, how to bridge through the VLAN and how to enforce this address to the packets. Okay, so that's basically what it is. Now, but basically by changing the format in the standard, which is a part of 802.3, that's the one that changes this format to this format. Okay, and registering that in 802.1Q, now you are in a position that you can implement a bunch of applications. What are those applications, or what are the benefits? You can partition your network in sub-networks. So you are making the life of the network administrator easier. You allow forming working groups. I mean, isolating people from one another. Enhancing network security. Okay? And providing a means for limiting broadcast domain. Means that if I want to broadcast, I only broadcast in one VLAN, not in the other VLANs. Okay. By increase of the number of terminals which is going around, now broadcasting gets more and more costly than the time that it was invented like 20, 30 years ago. Okay, so these are the benefits of VLAN, and that's how they implemented. Okay. Another, in fact, trick that they played in the Mac, in changing the packet format, was the so-called facilities that can allow you to do full duplex operation. That facility is creating control signals that they call it pause signal. Okay, but that pause packet or pause communication protocol, if you want to call it, is helpful for full duplex operation. Now, what is full duplex operation and why you need pause format? Full duplex operation, first of all, is defined by 802.3x. Okay? It was done around 1977, something like that. Okay? Full duplex operation was first, actually, type of operation which was using modification of the packet format. What is the purpose of full duplex and what is the purpose of half duplex? What is the difference? In half duplex, you have one line, you can send in either direction. In full duplex, with one line, you send only in one direction. Okay, so basically full duplex allows you to do point-to-point communication. Why do you need point-to-point communication? Because if I go to, like, carrier sense multiple access, okay, my throughput is always what? Less than 1, which means that if I have 100 megabit per second, I have always less than 100 megabit per second. Okay, and even when I have that 100 megabit per second, only if I have 2 transmitter receivers. Okay, now in full duplex operation, they disconnect the receiver and transmitter. They go to 2 different lines. So in each of them, they are going to have what? 100 megabit per second. In each of the lines, they have 100 megabit per second. Okay, and since that's like each of the lines, point to point, there's no carrier sensing. Okay, so it's just carrier sense multiple access is out of the way. So your data rate really drops to 100 megabit per second in one direction, 100 megabit per second the other direction. Okay, so that's what they do. That's the summary of full duplex operation. Yes.
This time is four LANs or just 2 LANs?
No, this is just 2 wires. One go to this direction, one go to the other direction. Now your question is good. Now, can you do that? Can you do full duplex operation to everywhere? No, you cannot. And we will talk about that a little bit later. What does it take to create a full duplex is, first of all, I have to change my jacks, my connectors. Okay? Because now the connector goes and comes back in different ways. Okay? Now, when I change it and I have what my packet format is the same as before. Okay? Now, how they do that? We go over that as we go a little bit further. So, in full duplex, the main difference is that you can simultaneously send information in both directions. So over the wire, you have like 200 megabit per second rather than 100 megabit per second. Okay, this is just the first thing. It's very useful if you have like 2 wires. Now, if you have 4 wires, what will happen? And especially you have 4 wires with the strange way that 802.802 the T4 is 803.3 T4, the 4 wires. You cannot do full duplex with them because the wiring is what is strange. But how about the TX? Yes, you can. Okay. How about the FX? Yes, you can. Okay. Then you go for the bus. How about the bus? Do you remember bus? Bus was like cables that everybody was hanging on. Can you have full duplex with that? No, you cannot. Okay. So there are a bunch of standards that you cannot use full duplex for. And there are a bunch that you can use for. And we will talk about that a little bit later. Which standards you can do, which standard you cannot. But the first thing is that traditional Ethernet does not support it. If you use it, you have 200 megabit per second. Adapter must have like full duplex connector. Okay. If you have repeaters, you cannot use it. Because if you have repeaters, repeaters are what? Collision domain. A bunch of people come to that repeater. Okay? So if you want to have full duplex, you must have what? You must have switches. Now, the other thing is that, as I said, as we discussed in a couple of minutes ago, it doesn't work with 100 base T4, doesn't work with bus topology. Okay? Now, since they are connected point to point, really collision domain is like, does not exist. There's just point to point connection. Now, what is the significance of that? If there is no collision, when we had collision, to detect the collision, we had to keep the number of bits 512 bits for the slots. Okay. Now the slots can change. Can change a little bit. You can either you can make the length of the packet longer, or you can make the length of the cables longer. Okay. So you can play with it a little bit more and cover longer distances. Now, these are like things similar to that. Throughput is double, permitting that's, I mean, I have repeated that in everywhere. Now, the efficiency of the link is improved because there is no collision domain. There is no collision and retransmission. Okay. Then, you don't need to have 512 bit. Okay. So, for example, if you have 100 base FX, limit was 412 meters that you could go in half duplex. If you go to full duplex, you can go up to 2 kilometers because you don't have collision problem in there or collision detection problem in there. Okay. So these are the advantages and things in there. Now, in order to implement that, now you come up to two sets of like standards. The standards in which you cannot have full duplex and the ones that you can use full duplex with. See, 10 base T, can you use full duplex? You cannot because it's bus. 10 base FL, 100 base TX, 100 base FX, 100 base T2, 100 base CX. All of these guys are the mediums that you can use with them, the full duplex. So the first one I made a mistake. 10 base T. 10 base T is point to point. You can use. Okay. But if you come to like 10 base 5, which was cable, bus, 10 base 2, which was bus, 10 base FP, 10 base FB, and 100 base T4, you cannot. Okay. So a bunch of standards which are not like any standard that can allow you. You have a wire in one direction, wire in the other direction. Means that you have two pairs of wires or even number of wires. You can apply it. Anything that is not like that is only one wire everybody hangs on, you cannot. Okay. Now, full duplex is restricted to point. So you have to have two end stations. Otherwise, you cannot implement it. So you cannot have medium access control of any sort. And the both of the stations must be capable of having full duplex, obviously. Okay. Now, in order to implement that, now the problem is that you may overwhelm another terminal. Okay. So now you have to have like a sort of flow control at the physical layer, not at the, usually we had the flow control at what? Logical link control. But we were disconnecting that. We were not doing any sort of flow control for the local area networks. Okay. Here, this pause frame is a sort of helping flow control at the physical layer. Okay. What is the story of the pause frame? Pause frame is a frame that when you send from one terminal to the other terminal, it's going to stop the other terminal from operation. And then pause frame has a timer which will identify how many 512 bits, how many slots you have to wait. Okay, so that's the story of the pause frame. Okay, now what is good about it, how they use it, first of all, how they implement it. It should be in the same format of regular frames that you're using for 802.3. You have to make some changes in there. Okay. Now, and then what you do is that, for example, if you have two links, A and B, and they are full duplex connected, B receives a lot of data from A, and it's congested. Immediately send a pause to the A to tell A don't send anything for so much of time. Okay, just to stop it. Okay, but the pause, when pause stops, when B stops A from transmitting, it still wants to allow A to send pause frames, because maybe that reverse situation occurs in between. So when you send a pause frame to another terminal, you stop that other terminal for sending any frame except pause. Okay? So that's how it gets like formulated. Then when you send a pause frame, you have a timer in there. Now let's say that you send at the first time a very long time, and now you are coming out of congestion. What can you do to let the other one to start sending again? You send a pause frame with 0 length of waiting. Okay, so actually it's a mechanism that you can control really the other end, whether you know how much time or you don't know how much time. Okay, so that's the purpose. And that controls the flow in both directions. Okay, so specification number 1 is that you are identifying a time, okay, and with that time you can start and stop as well. Okay. This number 2 is that when you stop another person from sending, then you are still that person can send a pause to you. It's reciprocal. Now, devices using auto negotiation protocol to discover that the other end has the pause or not. You have to always discover that the other person has the pause capability or not. That auto negotiation, which we said that in 100 base, they started to put it in. They use that for understanding the capability of the other end terminal. And there is another point about pause. Pause is a very dangerous thing, because if you want, you can sit in here and put my computer in Japan in hold. You can kill everybody around the world. It's a very, very dangerous thing. Okay? Now, in order to limit that danger, they won't let the pause go away from the bridges. So they keep it local. So as a result, another thing that you have to do to implement the pause is again to go to what? 802.1 and ask them to somehow handle this. So with that introduction, how did they handle this pause frame? This is the pause frame. The first thing that they do is that they have, again, preamble and a start of delimiter that we are not interested. Destination address, they have taken a MAC address, which is 0180C20000001. This is a specific destination MAC address. And they have registered that as a MAC layer, which is going to be used by 802 community only for pause. So now everybody knows that this address is the address of the pause. Okay, it's registered by what? 802.3 community first. Why did the 802.3 community? Because in 802.3 community, they are the ones who give the MACs away, MAC addresses away. Okay, so they say this one is reserved for the pause. And then they go to 802.1d. 802.1d is what? The bridge that we discussed when we talk about the bridges. In the 802.1d also, they register this MAC for the pause just to stop the pause. Okay? Just to stop it to go to the other places, other networks. Okay, so up to here, we are all set that I have like a pause frame, which is a specific MAC address that everybody can recognize that this is pause. Okay? Now, the second thing is that what you want to do with that. If a pause frame comes in, this is a control signal, really, in a sense. Source address is in there. I don't care about it. For the linked address, they pick up address 880x08. Again, this is something which is greater than 1500. This code will say that this packet is a control packet. So not only you can implement pause, you can do other things if you want in this same format. Okay? So now we are in a new world, really. We can do whatever control signal that we want and implement it if there is an application for that. But for the pause frame in particular, they have, so in here they have 8808, which is the address. Then they have 2 bytes for the opcode. 0001 opcode associates to pause. Other than that, you can use any instruction that you want. So up to here, I have created a mechanism for 2 things. Number 1 is a mechanism that is local, okay, for the pause. Okay. Number 2 is this is a mechanism that can implement what? Any signaling or control type of operation with the same format packets that I had originally, and it could not do these things. Okay. Okay. Now, what is the next problem? The next problem is that if this pause wants to work, the whole length of this guy has a minimum. Okay? Already I have, what was the minimum of the data length that I had? Was 46, if you remember. I already used 4 bytes, so I have to pad it for 42 bits. But those pad could be anything again. They call it reserved for anything. For the timing, they put it all 0, but could be anything else. Reserved for anything else you want to do in the future. Okay? And then the checksum is the same as what they had before. So the length what follows the minimum length. Okay? If you want now to compare this thing, this pause frame, with like this frame, which was your VLAN frame, your VLAN frame actually had added 2 bytes to the length of existing. So the maximum existing length was what? Something like, I don't know, 1508. Now it goes like 1512. So VLAN is increasing the maximum length for 4 bytes. But what the pause frame does is actually bringing the limit to what? To the minimum, which is the 512 bits minimum. If you have 2 bits, if you have a 2 byte, this is actually a little bit more than 512, because 512 is designed for 46, given that the addresses are 2 byte. And here you have 2 4 bytes on top of that. Okay, so that's it. That's the tricks that they have played. What is interesting about these tricks? With these tricks, they have really changed the Ethernet to a position that, number one, you can have control and signaling frames in there. Number two, you had 2 new applications really. One is the full duplex. The other one is what? Is VLAN. Full duplex, again, if you want to compare it, is the same as 82.5, point to point, even better, because it's bidirectional. Okay, so that's it. Now, we come back to that a little bit later when we talk about bridges. Yes?
Previous slide, we replaced the destination address with the standard address. How does the terminal know that this frame is destined for that? Like, we replaced destination address has its own significance. We started using it for something else. So how does the terminal know that this is for that particular destination?
At the beginning, if you want to use the pause frame, okay, you have to do auto-negotiation to see that both ends who want to use the pause, okay, they are aware of this thing.
So this is primarily for point-to-point.
Point-to-point. That's what it is. Now, okay. So that was 2 tricks on the Mac. Now let's go to the tricks that they have played to the physical layer, okay, of the Ethernet, to improve the Ethernet. The first one, as I said, is the natural one. ISO Ethernet means that you take the Ethernet and make it PBX. In order to make the Ethernet PBX, number one is that you want to put like an adapter cards, new adapter cards at 2 ends. And these new adapter cards should draw that 10 megabit per second that you were drawing earlier. Okay, so you need like 10 megabit per second in there to be compatible with the old one. Okay, compatible with the standard Ethernet. Okay, in addition to that, you want to put some sort of voice, so you want to increase your bandwidth a little bit. Okay, so the first thing that they do is that they increase the bandwidth from 10 megabit per second to something like 16 megabit per second. Okay. Number 2 is that they take the Mac and rather than CSMA CD, they put time division multiplexing. Time division multiplexing is a voice-oriented, excellent for PBX type of application. And just to have some numbers, I mean, with 10 megabit per second, you can have many, many users, hundreds of users. Okay, because each user is 64 kilobit per second in digital. And this is what 10 mega. Okay, so number of these things you can have. So why not I use that and I have a PBX system. That's the idea behind this. Now, the first thing is, okay, I want to be backward compatible. And in order to be backward compatible, I need 10 megabit per second asynchronous, 10 megabit per second data. And I want to increase it and add voice to that. What type of trick I can play? One trick that we have seen before is like change the line coding, the simplest thing. Over the same wiring, if we had Manchester coding 10 megabit per second, we saw that last week, if you use like 4B5B, now what would be your data rate? Manchester coding, if you have 10 megabit per second, your baud rate is what? 20 megabit per second. If now instead of Manchester coding, you use 4B5B, you get what? 20 megabit per second. time 4 divided by 5, which is what? 16 megabit per second. They are not exactly 16, they are a little bit more than that, because they want to fit these numbers to 64 kilobit per second, which is 1 unit for voice. Okay? So it's not exactly 20, it's a little bit more than that. So that's the trick. So the first thing that they do in the physical layer, the trick that they play, they switch from what? From Manchester coding to 4B, 5B coding. Okay? And with that, they go to like 16 megabit per second. Now, you take 10 megabit of that, you put it for the data, 6 megabit is left for what? For the voice. Each T1 carrier is 1.4. This is like 5 T1 carriers around. Okay? So it's better than T3. T3 was like 3 T1, 3 or 4 T1, 4 T1 carriers. Okay? This is more than that. Okay? So this is where we are. This is what they are doing. Actually, this is around that, around the T3. Around 4, yeah. This is around T3. Okay, so that's the trick that they are playing. Okay? Here we are. Now, technical specification is that it operates on Cat3, twisted pair, because originally we were talking about 100 meters and 10 megabit per second. They use 4B, 5B, and since now efficiency of 4B, 5B is 80%, and efficiency of Manchester coding was 50%, you go to what? 16 megabit per second. And that extra one is on top of the 10 megabit per second that you have. The next one is use TDMA frame at a clock rate of 20.48 megabit per second. That .48 is just to adjust this to like units of 64 kilobit per second. If you divide it by 64 kilobit per second, you end up with 320. Okay. You have 320 slots of what? 1 megabit per second. So you can have like 320 bits per frame. Okay. Each bit of that frame is how much? 64 kilobit per second. Do you follow that? See, I have like 2048. I divided by 64. I ended up with what? 320. Means that if I create packets of the length 320 bits, each bits of these packets is equivalent to 64 kilobit per second. Because I'm sending them these packets at the rate of 64 kilobit per second. Huh? Did you follow that? Okay. Now, so if I have a packet of length 320 bits, okay, and my data rate over the line is 20 times 48 megabit per second, what is the packet transmission rate? I get 20.48, I divided with 320, and I ended up with 64 kilobit per second. So these packets are going at the rate of 64 kilobit per second. So every bit in that packet, okay, the length of the packet is 320. Every bit is what? Equivalent to 64 kilobit per second. Huh? So what I have to do, I have to now come inside that 320 and I assign enough number of bits which supports what? The data rates that I want. Okay, that's what they do in here. They have like a bunch of packets or bunch of channels, they call it. Channels or portions of this 320-bit packet. Okay. Now, P channel is data. If you have Ethernet, and you want to have Ethernet and voice. ISO Ethernet says that you can use the whole thing for voice, or you can use 10 megabits for data, the rest for voice. Gives you two options. If you have voice, you have a slot which is 156.5 bits per time division multiplex frame. Okay, if you multiply that with 64, you are ending up to 10 megabit per second. 64 kilobit per second, you end up with that. Now, you don't need to have half a bit. You can have it in different frames. Okay, in one of them you can have 1, in the other one you can have half. This is the average rate. Okay. C channel, which is your isochronous, is 96. 96 times 64 kilobit per second is 6.1444 megabit per second. Equivalently, you can use 248 bit per frame, which is 15.872 megabit per second. How about the rest? The rest is for control and signaling. I need control and signaling channels. Where are those control signaling channels? One of them is D channel, which is 1 bit per frame, 64 kilobit per second. One of them is M channel, which is for maintenance, which is equivalent to 1.5 bit per frame, which is 96 kilobit per second. Again, remember, these are average. Okay. And then they have overhead and miscellaneous. 1 bit per frame for multi-service and 5.5 bit per frame for all isochronous. This is overhead of miscellaneous things. Okay. So this way, they have defined everything very fine for a time division mode, voice-oriented Ethernet. Okay. Again, when we were talking about this thing, it was mid-1990s. Remember the window of time. At mid-1990s, still people thought the future is voice-oriented. Okay? Still people were thinking about changing the LANs, integrating LANs into ATM networks. Okay? But today, it has changed a little bit. Anyways, ISO Ethernet did not become popular. Bottom line. Maybe because if you want to market this, people have already installed this thing everywhere. And for new buildings, you need new cards, and people then don't go for it. Okay. So if you want to change, the change has to be gradual. Revolutionary things has never taken place in the telecommunication industry. Always they had, like when they wanted to go to third generation cellular, for example, they were talking about evolution versus revolution. Wherever you were going, they were talking about evolution versus revolution. But they ended up to evolution. They evolved from existing things. Okay. But it could be a revolutionary step within the evolution. Okay. That's what they did in the Europe by going to wideband CDMA, but keeping their backbone as like second generation backbone. Anyways, that was another thing. So far I talked about VLAN, I talked about full duplex, and I talked as places that I changed the MAC, and then now I started to talk about physical layer changes. The first change that I told you was the change which was associated with 10 megabit per second actually Ethernet, or going from Manchester coding to what? To 4B, 5B. The second one, which is also interesting, is 100 base T2. You remember that when we were talking about transmission technique, I told you there are a bunch of tricks that people play. And I talked about it earlier in the last lecture. One of them is changing the line coding, which we did in that. The other one was what? To go to multi-level modulation. 100 base T2 goes to multi-level modulation. And we discussed that earlier a little bit, the type of modulation that they use in here. So I can go over that very quickly. Okay. In March of 1997, they came up to this 100 base T2, which is very bright idea at that time. Rather than having those 4 wires which are strangely connected to one another, I get 2 neat and beautiful like wires, and I put it in there with a very nice and sophisticated technology. But this is the way that it looks to us, not the way that it looks to the user. For the user, issues are different. But anyways, they came with this thing, and that was very interesting. what they are doing is that they take 2 pairs of wires and they go 100 megabit per second over that. Each of these wires is going to carry, they are like a Cat3, but they carry 50 megabit per second. So the same 100 meter that it was, okay, and then when it's 100 meters, they are going to add, rather than 4 pairs, they have 2 pairs. Do you remember what was the rate of this thing? I mean, in terms of bandwidth, was like 16 megahertz bandwidth almost, if you use binary. If you use binary, you can go up to 16 megabit per second. Do you remember? And then we said that if you go to trinary, okay, you have that 16 multiplied with what? Log 2 of 3, which is 1.5 or 1.555, depends on how you do the signal constellation. Whether you have equal or unequal points, okay? Around 1.5 to 1.6, which if you multiply that with 16, goes for baud rate of how much? 25 megabit per second. That we talked about it last time, okay? Now, in here, rather than 3, they are going to 5 levels. And rather than 1 dimension, they go to 2 dimension. Okay? So if you go to calculations, this is the calculation. Coming from that, the first part is coming from what we had earlier. Okay? In previous lectures, in lecture, I don't know, 2 or 3, when we were talking about transmission techniques. You remember that we had like, if you have a bunch of points in the constellation, you get the number of points, you multiply it with the probability of each point, log 2 of inverse of probability. And if you add them together, you get equivalent number of bits. You remember that? So if I have like 3 points with the equal probability, I have like 3 times 1/3 log 2 of 3, which is 1.5 something. Which is something that I multiplied with what? 16 meg, I get that one. Now, then, so if I come to 5 PAM, okay, 5 PAM, this is how 5 PAM is. 5 PAM has like 5 points. 5 points are like this. See, middle, here, 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 here. Okay, these 3, I believe, are with the probability of 1/4. These 2 are with the probability of 1/8. If I calculate the equivalent number of points for this, that's what we have in the screen of the computer. Okay, I have 2 points with the probability of 1/8, 3 points with the probability of 1/4. If I calculate this, I end up with 2.25. If I end up with 2.25, if I had 16 times 2.25, I can go up to 36 megabit per second. Over what? Over 100 meter Cat3. Okay. Now, equivalently, I can go to 2-dimensional PAM. 2-dimensional PAM, how does that one look like? This is 2-dimensional PAM that we saw that earlier. In 2-dimensional PAM, I have these 9 points in the middle, which are, in each dimension, they have probability of 1/4. So they have probability of 1/4 times 1/4, which is 1/16. Okay? Then I have 12 points in here. This one, this one, this one, and this one. These guys, in 1 dimension, they are 1/4. In 1 dimension, they are 1/8. So probability is what? 1/32. Because probability of point, you get each dimension multiplied with the other one. And then I have 4 points like this one, this one, this one, and this one. These are corner points, which are in each dimension with probability of 1/8. So they are in the probability of 1/64. Okay? Now, if I calculate the n for this, which is equivalent number of bits for this, I'm going to end up with 6.125. Okay? And bandwidth was 16. 16 times this is around 98, which is 100 megabit per second. Did you follow me? So I can take 100 meter of twisted pair and go to what? Go to 100 megabit per second. Okay? But I have to create a two-dimensional constellation. In order to create two-dimensional constellation, I need two pairs. Okay? One for the X, one for the Y. And that's what they have done in here. And I had given some introduction to that to you before. Now you understand it better. See, I can go over many things now in one day. Okay? That's why that I was spending time. Now, so I have two pairs of wires, really. One of them is X, one of them is Y. Huh? And these two pairs are totally carrying 100 megabit per second. So equivalently, I can say each of these are carrying what? 50 megabit per second. And that's what it is. This is 100 base what? T2. Isn't that nice? I can take this trick, play it in the other places. For example, if I have like shielded twisted pair or Cat5. For Cat5 100 meter, my bandwidth was what? 100. Is that right? You remember? If I use this one, like two-dimensional, okay, I can go up to like 600. Huh? So if rather than two-dimensional or go to four-dimensional, I can go to gigabit Ethernet. And that's what they do. Okay? That's how they are implementing that. But so far as 100 base T2 is concerned, I mean, all of the details we have covered before. So they use like 5 levels, plus minus 2, plus minus 1, and 0 volt. And then they have 2 wires. But how do they code them? Do you remember how do they code these things now? If you have 5 PAM, how do you code it? If you have like 4 points in the constellation, you assign to each point like 2 bits. If it comes 0, 0, you go with one of the symbols. If it comes 0, 1 to the other one, 1, 0 to the other one, 1, 1 to the other one. How do you want to do that in here? That one also I covered before, but I will repeat it one more time in here. In here, a fraction of the bits. Look at only the simple one. I want to have 5 PAM. 5 PAM was what? What I have now on my writing, on the handwriting. Remember, this is what I had for the things. I have 3 points in the middle, and I have 2 points in the corner. These are with the probability of 1/8. These are with the probability of 1/4. Okay? How I can, and data stream is coming. 0, 0, 1, 0, 1, 1, 1, 0, whatever. Huh? I get blocks of 2 bits. If they are 0, 0, 1, 0, and 0, 1, I get one of these 3 points. Okay? If it is 1, 1, I read the next bit. If it is 1, 1, 0, I go with this. If it is 1, 1, 1, I come with this. So the probability of the corner points are 1/8. The middle points are what? 1/4. And if I take the average bit, is the average bit that I calculated earlier for you. I ended up with what? Something like 2.25 bits on the average. Do you follow? Did you follow? This is very interesting. Now, what if I have two-dimensional? The same thing. I do the X and Y maybe separately. I get the first 2 bits, or first 4 bits. I categorize the first 2 bits of that. Then I may pick up the 5th one, or I may pick up the 6th one. Make sense? So that's how it works. And that's how it gets implemented. Okay? And then, if I take the average over like 2-dimensional, I ended up with average of the strange number, 6.125, whatever, number of bits. Because I have usually 4, but sometimes 5, sometimes 6 as a packet. So I get all of them, take the average, I go to 6.125. Okay? That's very interesting, isn't it? Now, by doing that, equivalently, I'm increasing my bandwidth. means that with the same bandwidth that I had before, because my baud is fixed, I'm stretching that with the coding. With the source and channel coding together. This is source and channel, both together are coded. Okay. Good, very nice. So we take this technology, it stretches now up to 6 times the bandwidth of one wire. Okay. Now I can go to higher dimensions. Okay. And this is the story about gigabit Ethernet. What is gigabit Ethernet? Gigabit Ethernet, they have an excellent website in University of New Hampshire. I have left it as one of the references in this lecture. And in there they have a few explanations. Because they have this laboratory which is like compliance laboratory for the local area networks. They had it for many, many years. People take their devices to University of New Hampshire. They look at the compliance. As a result, they have a lot of good, nice, deep, actually, things about local area networks. Now, we wanted to do something for wireless LANs in here. I didn't have the patience. I didn't have the staff. It needs a lot of patience, really, to do this thing. Actually, they suggested to us to do that like 8 years ago, something like that. Anyways, now, here is like what, these are coming from that website, a couple of these slides. Now, first one, this is what it is. I have a node in here, I have a node in here, and I have 1 megabit per second, 1 gigabit per second going in this direction, and 1 gigabit per second coming in the other direction. This is what they want to design. And then the whole idea is that in order to have this like data rate in both things, they want to comply with the error rate of 10 to the minus 10. Means that what? Any 10 to the 10 bits, only one error. But we discussed that. It's not that difficult, really. With a couple of, because the channel is either on or off. Okay. It's not a very difficult thing. It's not a nasty channel. As like, for example, long distance things. But, however, in order to do that, they require that they use adaptive equalizers. Adaptive equalizer is used in every voice band modem, commercial or personal. Commercial always, they are four line. They call it 4 lease lines. They have 2 to come, 2 to go. Commercial, the ones that the banks use for the modem. The ones that you use at your home, you are at 2 pairs. Okay? The commercial 4 wires, as well as the 2-wire modems, all of them, they use adaptive equalization. Adaptive equalizer was invented in 1960 by Bob Luckey, which later on became vice president of AT&T Research for many, many years. Okay. Anyways, they also used echo-canceller. What is echo-canceller? Echo-canceller is very similar to equalizer. What does equalizer do? Equalizer inverses the channel. So whatever is frequency characteristics of the channel, it inverses that. And it does it adaptively. Now, how about echo-canceller? Echo-canceller, actually, when you send your signal and the echo comes back, inverses that thing, if you want to call. Very similar. The algorithms are very similar to the adaptive equalizer. Where can you learn about these things? ECE534. And sometimes the ECE532. When I was teaching 532, I was teaching it in that, as well as in 534. But anyways, so, and then they have 3 next canceller. You remember what was next? That was interference between the wires. They have 3 cancellers in there too, because there are 4 pairs of wires. Okay? So now people are used to 4 pair because they used it for 100 base. Okay? Now they add cancellers to that. Okay? So you cancel your own echo, inverse the channel, and you have 3 cancellers, which is for the next. So you have 5 adaptive equalizers. Okay? And if you pair, so you have 20 of them for 4 wires. Okay? So 100 base T, is the motivation also for a bunch of studies in TIA, EIA, and ISO. TIA, EIA, and ISO, if you remember, TIA, EIA is the one that does the specification of the wires. Okay, so in there they talk about the next, fixed, etc. So they are talking about now fixed loss, return loss, crosstalk between bundle. Okay, but a bunch of study to create a standards for what? For interference between these lines. So now the lines are getting micro lines, very accurate lines. Okay, so this is like some of the things related to gigabit Ethernet. The format is again like you want to be compatible with 100 and with the 10, and you can connect everything together. Basic idea about modulation technique. This is a good chart for that, similar to the other chart that I showed you earlier. Earlier, I was have to wait a little bit. Okay. The earlier chart that I was talking about was this chart for 100 base. Equivalent to this chart for 100 base is this chart for 100 base for the gigabit Ethernet. Basically in here they have the same coding, like 8B, 10. I mean in there you had 4B, 5B. In here they have 8B, 10B. Okay. After 8B, 10B, they come to the fiber, two type of fiber, LX and SX, and then they come to the cable, to the copper, which they call it CX. Okay, but directly they go in there. There is no ML3 in here. Okay, this is one way. The other way is that you take the data, you do 4D PAM5. Now you understand what is 4D PAM5. You have seen the 2D, 3D you can sketch, 4D you cannot sketch. You have to imagine the 4D. But basically you have 4 wires, each of them have 5 levels. Each of them have 5 levels. Okay. Now, this is an unshielded twisted pair. Okay. So the only thing that you need to know now is that what are the length of the cables that goes with each of these things. For sure, they are not going to be the lengths that you had before. Okay. So what you can do, either you reduce the size of the line, okay, or you go to complex modulation techniques. The next chart gives you those type of things. These are over fiber, variety of fiber, and these are the lengths. They cover up to 5,250 meters on 1 gigabit, depending on the type of fiber that they use. Okay. If you go to Cat5, which is the good one, Cat5 you were going up to what? Up to 100 meters. In here you have up to 100 meters. Okay. Now, then when you go to the shielded cable, okay, and they don't have for Cat3, okay, goes only up to 25 meters. Okay, so they have compromised on the length. Okay, now there is a summary which is coming from Tannenbaum's book, which has all the lengths. So either you have like 4 pair of unshielded twisted pair which goes 100 meters. You have fiber which can go to 5,000 meters. You have fiber which can go to 550 meters. You have 2 pair of shielded twisted pair which goes to 25 meters. Okay. But remember that this is Cat5 unshielded. There is no Cat3 in here. Okay. And these are the 3. These are a little bit more detail about like summary of each of those standards that I took it from the TechFest. TechFest is excellent for updating on the local area networks. And this is that how the 8B, 10B works. Okay. And the last chart in here is the scrambler that I told you earlier. Another thing that they use in this gigabit Ethernet is the scrambler that we discussed that several times up to now, but I never showed you what it is. This is what a scrambler is. A scrambler is something that any data which goes in comes out random. So it creates a lot of transitions. If you have a lot of transition, it's good for detection. Okay. Whenever you go to very high data rates for cable, or you go to the radio, okay, then you have a lot of jitters that you cannot follow. The scrambler helped to reduce that. Voice band modems, all of them, they have a scrambler. All the voice band modems they have, because they operate over what? These lines, which are very bad lines. They have a lot of noise, and they have a lot of distortion. Okay? But local area network up to 10 megabit, beautiful. You go to like giga, now you're like a little bit under pressure. Huh? Now, this is why they use a scrambler. A scrambler is a state machine, really. This is a state machine. These are delay lines, and this is exclusive OR. They come in here, the data stream which comes in, one exclusive OR in here, comes in this state machine, exclusive, comes back. And at the receiver, exactly reverse of that. Very nice coding for that. Okay. So these have been developed by what? Those who were working on the coding theory in 60s, 50s, and 70s. They have found a lot of nice structures. One of them is this type of scrambler type of thing. One of the nice application of the coding theory. The other application that we are using is what? Trellis code modulation that I told you, which I don't go over that. That's also very, very nice. Very, very good application of coding. Now, it seems that to understand like physical layers, at least an understanding of coding is very good for you. Okay? If you want to understand that. Now, which course you can go for that? Again, 532. 532 is a place that, actually right now Al Lovek is teaching that. Al Lovek, his area of research is like coding theory. He became a fellow of IEEE because of coding theory contribution. So, and he has a textbook, very popular actually book that he wrote with Michelson on coding. So when he teaches 532, you will learn a lot of coding from him, I assume. Okay. But I have bias because he's my co-author too. But he's very good, excellent. His course is very good, 532. A lot of students are like have taken that and they like it, if you are doubly in particular. Okay? And this is like details of how those like state machines work, which is not important. This is, again, details of 100 base T in a different format, really, summarized, coming from TechFest. These are references that I used for this lecture. One was the textbook that we have. One is this book called Fast Ethernet by Johnson. One is TechFest, which I used a lot of it. One is a paper on 100 base T2, which was published by these guys. These are from IBM Richlecon Lab in Switzerland. And then this is the website at University of New Hampshire. The last announcement is that I have added some interviews, audio interviews, in the website, which are with, one of them is with Brian Sylvester, he's a graduate of WPI, with a lot of experience in local area network design. The other one is with Jeff Dye, which is CEO of GCD, which is manufacturer of wireless LANs, local, one of the leading actually manufacturers of the worldwide leader right now. And then the last one is with Marie-José Montpetit, which was the chief architect of Nokia's home networking division. But Nokia has closed that division now, but she's very knowledgeable in home networking. So I have 3 interviews now that you can listen to them. Each are about 5 minutes, something like that. Okay? Very good.